and a lot of this chapter is on the next test. Next week will be 2 days of chapter 9. The week after that, we'll do a review, and the week after that, we'll have a test. So there'll be a test about a week before Thanksgiving on chapter 7, 8, 9. This is one of the chapters on the next test. Just quickly, we're past the halfway point, and when we take the next test in the middle of November, we'll be 3/4 of the way through the semester. What's the expression? Time flies when you're having a good time. I'm going to go a little rapidly at the beginning here, but I expect everybody who was absent to take copious notes. Then I'll slow down at the end. We may go right close to 3 o'clock today, but I'm not doing this chapter ever again because we have a lot more to do on other chapters. Everybody ready? Okay, let's go. Okay, switches work at data link layer 2. Know that for my test. Now, remember what I said. Last week was the 7 layers. I'm never doing the 7 layers again. But I said from now on, they're going to just simply assume that you know all the 7 layers. Well, wait a minute, I don't really know them yet. Well, that's your hard luck because they're assuming you do. Switches work at the data link layer 2. Why? Frames and MAC addresses. Frames are at the data link layer 2. MAC addresses there. Switches use MAC addresses. Peter Piper picked a peck of pickled peppers. Okay? Know that switches work at the data link layer 2. Right? Okay, they're telling you that each switch connection is a collision domain. Let me try to explain this in plain English. If I'm connected with a hub, everybody here could collide with everybody here. Well, when I connect this guy with a switch, this guy could not possibly collide with this guy, who could not possibly collide with this guy. Every port on a hub is the same collision domains, or anybody connected to a hub could collide with somebody else. Every port on a switch is a separate collision domain, or everybody connected to a switch could not possibly collide with anybody else. And why? Because the switch forwards it only to that port, to no others. Okay? Switches separate collision domain, or what it says, each switch connection is a collision domain. Now, again, I'm going a little rapidly because the people who were here heard this last time. Those who were not, you better take unbelievable notes because I'm going to slow down toward the end. I'm not even going to talk about this slide. I haven't got time. I'm not going to talk about this slide either. I did last time. I just don't feel like it. Okay, but this slide I am going to talk about, the switching table. Okay, top dot, switching table has MAC addresses, routing table has IP addresses, right? I would want to know all that stuff. The second dot, when the switch is first powered on, it's empty. Now, again, I'm going a little rapidly because the good people have heard this before. They're just updating their notes. So, when the switch is first turned on, I send the frames to everybody. You say, wait, Professor, I thought you said you only sent it to one person. Sure, and here's the big one down here. As the network devices send frames, the switch reads each frame's source address and adds it to the table. So remember my thing from chapter 1, 2, and 3. We forward packets based on the destination MAC address, but we build a switching table based on what? The source MAC address. The switching table is built based on the source MAC address, and the frames are forward based on the destination MAC address. If the frame's destination MAC address isn't found, I forward to all the ports. What do you mean all the ports? Why don't you forward to the right port? Well, if the MAC address is there, I only forward to the right port. If the MAC address is not there, then I got to forward to everybody because I'm not sure. Well, you're going to keep forwarding everybody? No, eventually I'm going to find out where you are. And then when I know where you are, then I'll forward it only to you. Switching table, MAC addresses, frames. Data link layer 2. No. Now, is this a new lecture? It is and it isn't. We covered this in chapter 3, but now we're looking at a different way in chapter 8. And I'm never doing this lecture again. Okay, this is simply one port can have several MAC addresses. Now look, here, that's not possible. This port has this MAC address, this port has this one, this port has this one. But up here, port 1 goes here. Port 1 also goes to here. And port 1 also goes to here. So in this table, port 1 goes to this MAC address, port 1 goes to this one, and port 1 goes to this one. Can a table have multiple MAC addresses for a single port? And the answer is they can, and they do in this case. Do they always? Of course not. Could they? They could. Anybody who was absent last time should be paying very close attention. Okay, this is one of my favorite ones. First of all, it's interesting, the top dot and line that it says, We know switching tables contain MAC addresses. How many? 8,000 MAC addresses on a switching table? Well, that's atypical. You wouldn't have that many, but that many could be in it. Now, let's talk about stale entries and aging time. How do I build a switching table? By the source MAC address. I get a frame from you. I say, oh, there you are. I log you in, that's you. But I put a timestamp on it because I'm saying you were there as of 20 minutes ago. If you were there as of 20 minutes ago, you're probably still there now. But if you're there as of 3 days ago, you may not still be there. See what I mean? So I age it out. If the timestamp isn't updated within a certain aging time, it expires. I don't want to have what's called a stale entry. And a stale entry means I found out where you used to be, but I have no reason to believe you're still there because I haven't heard from you for such a long amount of time. You see what we're doing here? This is not a new lecture exactly. The rules we learned in chapter 1, 2, and 3 were general rules. Now we're detailing them. Now we're talking about the timestamp, the aging time. How many MAC addresses can it take? How long can it be held? 8,000. This is just details on the things we learned in chapter 1, 2, and 3. Right? By the way, I'm very happy with this class in general. I think you're a smart group, and I think you're going to catch on to this and do well. Some of you are not, but most of you are, so keep it up. Again, I'm going a little rapidly because we did it last time. Now, hint, hint, hint. For those people who were here last time and those who weren't, this slide will definitely be on my next test. So let's go through this very slowly. How do I normally forward and switching? I do store and forward switching. I read the entire frame. I examine the entire frame. I look at the end and the beginning of the frame, and then I forward it. Here's the frame, it goes to you. Here's the next frame, it goes to you. Here's the next frame, it goes to you. Store and forward switching. What am I doing? I'm making sure it contains no errors at all. So this is perfect. I never forward errors, and it's extremely reliable. But there's a kind of cuidado on it. What's the cuidado? Could you go a little faster? I can't go any faster. I got to examine this frame check sequence, make sure it contains no errors, and I got to forward it. That takes a certain amount of time. Let me suggest something. What if you do cut-through switching? What if you read only enough of the incoming frame to determine the source and destination, then send it on? Then you're not making sure it contains no errors. You're just sending it on. And what's the disadvantage? You're not doing error checking. You might send a frame from me to you, and I say, oh my God, I never should have sent that to her or to him because it's a damaged frame. Well, idiot, why didn't you know that? Well, because I never looked at it. I just did the to and from and sent it. Wouldn't it have been more responsible to do this? Well, here's the thing, yes and no. This gets it there faster, but there's no error checking. This gets it there slower, but there's plenty of error checking. And this is the middle one, where I read enough of the frame to guarantee it's a minimum size. I send it up. This one, I minimize the number of errors, but I don't get rid of them altogether. With this one, there's no errors at all. With this one, there's fewer errors. With this one, all the errors are forwarded. But that's the fastest, that's the slowest, and that's in the middle. So all three of these are on my next test, but I'm not done with this. Let's go to the next slide. Here it is. Store and forward. I examine the entire frame, so no errors are forwarded, and it's very slow, most reliable. Cut through. I don't examine them, so I forward all the errors. But by not examining them, I can go super fast. That's the fastest, but I forward errors. And this guy's in the middle. I forward some errors, and I go faster than this, but slower than this. Hint, hint, hint. Know all three of these for my next test. Now I'm going to move on in a minute, but those who were here last time has heard this lecture now twice. And I need all three of them for my next test. I'm just pausing. I assume there's no questions. I'll be doing a review for the test, but I'm never doing this lecture again. Next week, we're going to chapter 9 and doing all that. And the following week, chapter 10, the following week, chapter 11. So, but we're getting there. We're halfway through now. When you take your next test, we'll be 3/4 of the way through the semester. Merry Christmas, everybody. We're almost there. Or happy Halloween, I should say. Okay, know all three of these. I now want to move on. And there's that one, and we want to know it. Okay, I got to do all these terms. I'm going to do them a little bit rapidly. And then when I get to the next couple of slides after that, I'm going to slow way down. Okay, it's 3:30, and we'll be out of here by, not 4, but by 4:15 or so. And one more time, we're never doing this chapter again. So, it says that high-end switches have blah, blah, blah. Let me paraphrase all that. All switches have multicasting. All switches have spanning tree. All switches have VLANs, and all switches have port security. 2 of the 4 of these will be on my test. I forgot which 2, but let's go through them. These are things that you found in switches that all switches have today. And multicasting is the easiest one. So here it is, and this would be a perfect test question, hint, hint. What's a broadcast? Everybody on the network. What's a unicast? Just you, just you, just you. Unicast, one person. Broadcast, everybody. Well, what's a multicast? A group of you. Not everybody, not nobody, but just this aisle, just this row, just you 4, just you 6, just you 2 over there. That's a multicast. And what I do is, this is a little bit tricky. I have a special registered multicast address that people listen in on. So I'm really sending the frame to one address, but 3 or 4 people listening in on that address. Multicast, a group of people, not everybody and not one person. More than one person, but less than everybody. And I'd say today, all switches have this ability. Okay. And that would be a perfect test question. What's the term multicasting? Now, this is another perfect test question. Hint, hint, hint. Okay. What's a spanning tree? Well, I don't want a switching loop. What's a switching loop? When a frame is forwarded from one switch to another, I'm trying to go from me to you in the back. So I went from this switch to this switch to this switch, and it's going to hit you in the back of the room. But for some reason, it misses you in the back of the room. What does it do? It keeps coming around and comes to me again. But the destination address isn't me, it's still you. So it sets out to try to find you in the back of the room. It gets near you. For some reason, it misses you. It comes back to me. What does it do? It sets out to find you another time. So it's like a dog chasing its tail. It's in an endless loop. I'm going from one switch to another, an infinite loop, trying to get to you. For some reason, missing you and going around and around. What does STP do? When a loop is detected, it goes into blocking mode, preventing and forwarding frames that would make the loop. So I see a loop going around and around. The STP says, let's block that port. Now the loop stops here. It can't keep going. It stops. But now I've broken a connection. I can't do anything. So if the loop configuration is broken, the switch then resumes. Now I resume forwarding frames. Where I resume? Because I assume that the second time it's going to go through to the right person. And it generally does. Well, wait, Professor, what if it doesn't go through the right person? What if it goes on another loop? Well, it blocks again and then unblocks it. So it is a piece of software. It's a program. It's a subroutine that runs on a switch that's designed to prevent switching loops, which are also called broadcast storms. I want to prevent a switching loop or a broadcast storm. When the loop is detected, it automatically blocks that mode, stopping the loop from happening. All switches have STP. It's just that they're not always turned on. So you may have to tell the switch, yes, I know you have this capability, but with a Cisco command, enable or turn on STP, and then it will do it. Again, this whole course is technobabble. What is multicasting? What is STP?
Sir, I have a question. When you mentioned broadcast a storm, does it mean that it helps prevent a bad signal from weathers or temperature?
An endless loop and a broadcast storm means I got packets going all over the place. It's not so much a bad signal. I'm trying to prevent a frame that was lost and is going around an endless cycle. Look, we don't want any extra spare traffic. So I'm trying to send to you, you're trying to send to me. And there's all this garbage of somebody circling the thing. I'm trying to get to you, you're trying to get to me. Who's this idiot circling? Well, I want to get rid of the garbage. See what I mean? So it's like you're trying to get to downtown to shop. And there's some guys cruising the block looking for girls. So they're going round and round the block, and you're trying to find shopping. Wouldn't it be great if those guys would just park their car and be less traffic? I don't want these endless loops blocking all my garbage. You say bad signals. An endless loop is a lost frame that's going nowhere. And I don't want it clogging up the network. So I want to detect it, block it, and stop it from happening. Does that answer your question, I hope?
Yes.
All right, good. Let's keep going.
Thank you.
Right. Okay, and there's that. STP slows you down, but so what? You'd rather slow down. Well, here's how I'd say it. STP slows you down, it's true. But for Joe, who just asked, Joe Lopez, if I have an endless loop, that can crash my entire network. So I'd rather go a little slower and be up and running than be going real fast and then crash completely. You know what I mean? So we're generally willing to live with STP, slowing it down. Now, what's a VLAN? And this is something you really should know. So I don't know if it's on the test or not, but you really should know it. A regular LAN is you're local to me. You're next to me. I can poke you in the arm. I can throw a spitball at you. A virtual LAN means you're nowhere near me, but it's if you were close to me. So let me see if I can do this. I'll come to this one. If this guy, VLAN 1, and this guy in this building all wanted to work on LAN 1, the only way they could do it is you'd have to get the moving men to move them. And they'd all have to move to a room in either this building or this building. But this guy says, I want to stay here. 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 But I want to work as if we're together. Well, the regular LAN, it doesn't work that way. A regular LAN is actually local. They got to be next to you. But a virtual LAN is this. I'm going to pretend I'm in the same room as you, but not going to be there. So that means that this guy and this guy and this guy and this guy can all talk to each other as if they were in the same room on the same local area network, even though they're in separate buildings. And this guy and this guy and this guy, VLAN 2, can all talk to each other, even though they're in different buildings, as if they're in the same room. But here's the cuidado for my geniuses. This guy can't talk to this guy. Why not? They're in the same building. Why can't they? Because they're in a different virtual LAN, and you can't connect LAN to LAN unless you do what? Unless you go through a router. So a virtual LAN is simply, instead of moving you physically into my room, I pretend you're in my room, even though you can keep your office with a view. And the only way VLANs connect is with a router. So here it is. Switches create VLANs, routers connect VLANs. One more time. Switches create VLANs, routers connect VLANs. Now, I'm about to slow down in a minute because I want to get, this is the sexy part of the lecture. It's going to take me a few minutes. But I'm doing one more slide that I want to do on this that's still important. And well, I'm not going to go over this. Don't use VLANs unless you really have to use them. In other words, VLANs will slow you down. So here's my thing. If you need a VLAN, use it. If you just say, gee, VLANs are neat, let me put some in. No, you're wasting your time. You only put a VLAN in because there's a reason. This guy, this guy, this guy need to work together and they can't move. Then you put one in. If they're not working together or they will move, then don't put one in. Okay, but here's the one I want to just talk, and I'm skipping this one, is this one here. There's a term called layer 3 switching, and this is very important because it's an oxymoron. What's an oxymoron? A self-contradictory term. So here it is. Switches work at layer 2, switches only work at layer 2. Routers work at layer 3. One more time. Switches work at layer 2, routers work at layer 3. Well, wait a minute, Professor. Didn't you tell me about a layer 3 switch? Doesn't that mean the switches operate at layer 3? No, that's a trick a term that's supposed to be directed to people who really know what's going on. Let me see if I can follow the logic because it's very important. If I tell an experienced person I've got a layer 3 switch, what immediately goes off in his mind is, wait a minute, you must be some kind of idiot because I know the switches operate at layer 2. What do you mean you got a layer 3 switch? What it means is I have a switch. It's operating at layer 2 like they all do, but I've got some layer 3 routing capabilities added to it. It's a layer 2 switch with some layer 3 routing capabilities added. Switches do not operate at layer 3, even though there's a concept called a layer 3 switch. And again, something else for the people who were absent last time. Remember my brilliant lecture last week? What was that on? All people seem to need the data link layer, network layer, presentation layer, etc. We're now assuming that you know the layers. Gee, I just learned them two days ago. How can I know them? I'm telling you, the next test is going to assume you know your layers code, and you better know them. So one more time, switches only operate at layer 2, the data link layer. All routers operate at layer 3, the network layer. Is there such thing as a layer 3 switch? Quotation mark. It's a layer 2 switch with some layer 3 routing capabilities added. That's all it is. Now, for those who follow what I said, I want to get to the next thing. This is a neat slide. Watch what happens. When these were all one person, they could have talked to each other. Because I divided into VLAN 1 and VLAN 2, these guys can talk to these guys, and these guys can talk to these guys. But for this guy over here to talk to somebody in this circle, we have to go through a separate router. Well, I'm kind of stingy. I don't want to buy a separate router. Well, if I've got a multi-layer switch, this allows these guys to talk to each other. This allows these guys to talk to each other. But if this guy wants to talk to this guy, he goes through the router part of that multi-layer switch. That's the layer 3 switch. I don't have to buy a separate router because the switch contains a router within it. Peter Piper picked a peck of pickled peppers. I'm sorry, people, but this is the course. I'm assuming the smart people know exactly what I'm doing, and some of the other people are a little bit lost. Okay, now I'm going to slow way down, and here's what I'm going to slow down. Let's begin. Routers operate at layer 3. Now let's remind ourselves, layer 3 is the network layer, layer 2 is the data link layer, and layer 1 is the physical layer. Remember? The IP address is at the network layer, layer 3. The MAC address is at layer 2, the data link layer. MAC address, layer 2, routers, MAC address, layer 2, frame switches. IP address, packets, layer 3, routers. Routers operate at layer 3. Okay? What do routers do? They connect LANs. The middle line is very important. Switches always forward broadcast. Routers never forward broadcast. One more time. Switch a broadcast is like calling low cards, everybody. Switches always forward broadcast. I'm sorry, was that Mr. Lewis? Okay, I think I saw the guy, Mr. Lewis. I've had to mark you in a minute. So, one more time. Switches always forward broadcast, but the middle dot here, routers never forward broadcast. If you send calling all cars to a router, you know what takes that packet? You want me to show it to everybody? Here's what I'm going to do. I'm going to put it in the trash can. Well, wait, I told you to send to everybody. But I'm a router. Anything that goes to everybody goes to nobody. And why? I don't want to screw you? No, because I don't want to have a broadcast storm. I don't want to have a lot of runaway packets. If I sent a broadcast over the internet, that would mean every computer on the internet would have to get it. Do that once, twice, or 3 times, and the entire internet would crash. Right? No, which layer which operates on. Okay, now this one is tricky. I did it last time, but I'm going to go very slowly. Let's see, it's 3:44. Yeah, we'll be done at 4:10 or 4:15. But I'm going to do this very slowly because it's complicated. Even if you were here last time, I want you to pay close attention. If you were not here last time, I want you to pay super close attention. So I'm going to skip around like I did last time. Okay, so I want to go from 9 to 5, network 9 to network 5. The point is I can go through different routers. I could take this path through router C, or I could take this path this way. There's several ways to go from here to here, okay? The idea is if I normally go this way through C, and C is down today, instead of not being able to get there, I'll just take a different path. Routers connect networks in many different paths. That's why if I want to send a packet to California and my normal routers are down, I can't go to California, I just take a different route and I can get through. And that's why the internet doesn't crash, because the internet has so many redundant paths. Let's keep going. Okay, I'm going to skip this slide, but paraphrase it. They say here when a router receives a frame, it compares a blah, blah, blah. But I want to make it clear. Routers don't use frames. Routers use only packets. Now you say, wait a minute, the router's receiving a frame. Yeah, when it goes into the router, it may be a frame because it has the MAC address on it. But the router can't use the MAC address. So the router immediately strips it down and it processes the packet, not the frame. See what I mean? The router may accept it as a frame, but it forwards it only as a packet. What is that called? It's called packet forwarding. So when I'm sending some data, my term paper, from here to California, where's it going to? It's going through a bunch of routers. How is it going from here to California? As packets, not as frames. And how is it getting there? As packets, not as frames, with frame forwarding going through what? Going through routers by IP address. Now look, I'm starting to use a lot of jargon and lingo. Those who were here in chapter 1, 2, and 3 and were actually paying attention, you now have a really good idea what a packet and frame is, how different they are. You now know what the MAC address, IP address is, how different it is. If you still don't know that stuff now, you might want to consider another career. The point is, you do have to know that. You do have to be familiar with it. I'm starting to use it as if you knew it. Routers only forward packets based on IP addresses. Yes, it may go in as a frame, but it's not processed as a frame. Right? Okay, I'm going to skip around now and do what I did before. So let's go to, I'm going to come back. Let's go to this one here. So router A, there's 2 LANs. There's router B. There's 2 LANs connected. There's router C. So routers have one magic ability. When I turn on router A, it automatically can say, That 168.1, 168.2, it's there. How'd you know that? Are you a genius? Look, I'm not an idiot. I just reached out and all the things connected to me I can sense. So I can read that 168.1, 168.2, and 168.3. I can read them. Why? They're there. I can touch them. Well, how about this guy? Well, I don't know anything about this guy because I'm him. This guy says, I can reach out and touch this person. See what I mean? And this guy says, I can reach out and touch this person. Now, here's where it gets sexy. Pay attention. I'll show you mine, you show me yours. These two routers take up a conversation. And router A says, I know about 2 lands. Would you like to hear about my 2 lands? And router B says, well, I know about this guy. Would you like to hear about that? So now this guy tells him about 168.1 and 2. And this guy tells him about this. Now suddenly this guy knows this guy's here, this guy's here, this guy's here, but he also knows these guys are here. Well, how does he know they're here? Because he told them. So now he says, that's a good deal. Let me reach out to you. I know about several routes here, and you know about several. You tell me yours, I tell you mine. So now router B knows about this guy, this guy, this guy. He also knows about this guy, and this guy. How do you know about them? Because he told them about them, and he told them about him. So the routers now know about every other LAN they're connected to, partly because they sense it and partly because they're told. Now, because this is my second lecture on this, I'm going to do it out of order. Watch carefully. This is a Cisco routing table. Now look what it says. CCC, 68.4, 68.5, and 68.3 are directly connected. It took me a few minutes, but the other class showed me this is this router. Why? 68.3, 68.5, 68.4 connected. So it knows about those 3. Oh, wait a minute, Professor. How does it know about all these other guys? It knows about these other guys because this guy told them and this guy told them. So the R actually stands for the RIP, the protein call, but it also means remote. I learned this from somebody else. I learned this from somebody else. This one I figured out myself because I'm directly connected. This one I figured out myself, I'm directly connected. These 2 or 3 I learned from somebody else, but this guy I'm connected to. You know all the networks you're connected to because you can reach out and touch them, but you know all the networks you're not connected to. Why? Because somebody told you about them. Not somebody, some other router. Now, that's the key to this next part of the lecture. How do the routers talk to each other? How does this router tell this router about stuff? That is, and I'm doing the lecture a little out of order this time, but it's a second lecture. That's a routing protocol. So the routing protocol is the language that routers use to say, you show me yours, I'll show you mine. I'll tell you about my direct connections. You tell me about yours, and now we'll have a lot more. And then you over there, you tell me about yours. And then you over there, you tell me about yours. By the time I'm done, I know where whole bunches of lands are because you told me something, you told me something, you told me something, you told me. That's the routing protocol. A set of rules routers use to exchange information so all routers have accurate information about the network. Now, hint, hint, hint. Here's the part for the test. Right here. There's 2 kinds of routing protocols, distance vector and link state. Let's do it several ways. Distance vector, the old one, the crummy one. Link state, the new one, the better one. So let's do this lecture very slowly. Distance vector. When I get a routing table, I send my entire routing table to you, and you send your entire routing table to me, and now we know about each other's information. That's easy. End of story. But what happens then is, after I'm up a while, all of a sudden my routing table changes. In other words, one of my routes I thought was there got broken, fell apart. Another route I thought was not there, somebody plugged it in, it came up. So now I've got to tell you my new routing table. Well, with distance vector, I send an entire copy of the routing table every time. So if my routing table gains or loses one line, I give you the new copy of everything. One more time. If my routing table gains or loses one line, I give you an entire copy of it. Now, does that work? It sure does. You keep up to date by doing it. But I'm doing a lot of extra work, but it does work. And for years, that's all we had. Now, distance vector, link state is a little bit different. When you first turn on, every router sends its entire routing table to every other router. So here's all my stuff. Give me all your stuff. We got it. But this time with link state, if I get a change, I only send a change. So instead of sending the entire new routing table, I just say, hey, delete line 5. Hey, add this to line 4. Hey, delete line 6. Hey, add this to line 1. I only send the changes. It's more efficient. Okay, we're done? No. Here it is. What's convergence? Convergence is when every router knows everything about every other router. Let me do that again. When every router knows everything about every other router. So when I have all the accurate information on my router, and this guy's got all the proper information, this guy does, and every router's routing table is up to date, it's in convergence. We got there, right? Well, it's a problem. As soon as we get there, oh, wait a minute, this route just went down. Oh, wait, you know this route was broken? The repairman just fixed it. It's now up and running. Oh, wait, this one that used to be running isn't running anymore. Oh, wait, that one over there also got fixed. He's up and running. So every time you think you're in convergence, another route goes down or another route comes up. So you're constantly doing this background chatter telling it. What is convergence? How fast the routing tables of all routers are updated. And how on convergence, oh, that's the speed of convergence. Convergence is when every routing table is up to date and accurate. Okay, let's go slowly. Distance vector. I send the entire routing table. What does that do? It's a lot of network traffic because sending an entire copy table is higher network traffic. And do I converge? I do converge, but it's kind of slow. Now, here's the punchline for the geniuses. With link state, I only send the changes when a change occurs. I just say add a line, delete a line, add a line, delete a line. Well, what does that mean? A lot less traffic, right? And I converge faster. So link state is only send the changes, less traffic, faster convergence. Distance vector, send the entire table, a lot more traffic, and a lot slower convergence. Peter Piper picked a peck of pickled peppers. I can already do a mind read. I know I'm talking to some very intelligent people. By the way, a lot of you think this is tricky and hard. This is really how routers work. And if you take a Cisco course, you'll have to do all the details and all the commands. Here we're just getting concepts. So it may seem slightly difficult, but it's kind of important that you have these concepts down. Because in the job interview, if you don't have these concepts, you're out. Okay? All right, so everybody knows what convergence is, and here's the other part that I'm pushing. What a routing protocol is, and then the difference between a distance vector and a link state. The distance vector is the old one, the crummy one, the slower one. The link state is the new one, the faster one, the speedier one. See the difference? And you do have to know that. And again, this is the second lecture I'm doing, and I'm slowing down. I'm going to keep going. We have a lot more to do. We should be out of here by 4:10 or 4:15. And we're never doing this chapter again. We have an equally difficult one in chapter 9. Just a bit of good news. We're already halfway through the semester, and we take the next test, we'll be 3/4 of the way through the semester. So I hope you're all enjoying yourselves. Well, it's hard for me to believe. I mean, I think we started this, and now we're at the halfway point, going to the 3/4 point. It seemed like it was just summer a few minutes ago. All right, I'm going to keep going nice and slow. Know the term convergence for my test. I don't want to talk about this, just quickly. They talk about gateway protocols and border protocols. You just won't be on a test. I'm just going to explain it to you quickly. When they talk about routers crossing borders, they're not talking about, you think of crossing a border, United States to Canada. Well, there's another border, New Jersey to New York. Well, they got another border, Bergen County to Passaic County. Routing borders are not that. Routing has what's called an autonomous system. So here's an area of the router. Now it's not Bergen County or Ridgewood or Secaucus, it's just an area. When I cross from one routing area to another routing area, I'm crossing a border and I need a border protocol. Well, what do you mean you crossed the border? Did you cross a state border? No. Did you cross a city border? No. What about a county border? No. You crossed a routing border. So border gateway protocols talk about crossing routing borders, and they have nothing to do with city, state, or county borders. That's all I'm going to tell you. And I'm not going to talk about this because you would learn this in a Cisco course in detail. Well, this won't be on any test. Okay, I have to talk about that for 1 minute. And that is static routing. Can you type something in? And the answer is you could, yes. You seldom do. Can you type something in? Yes, you could. I'm going to do, yeah. I'm going to go back and just show you something quickly. I skipped a slide on purpose. And this was the slide I skipped. No. Yeah, this one. So how a route can divide is 3 ways. Well, what's the first way? Network is connected directly. Well, we said that. It can reach out and touch the one. What's the second way? It's entered dynamically by the routing protocol. In other words, this router told me, this router told me. So to me, those are the 2 ways. That's it. Well, wait a minute, Professor. There's one more way. It says there. It says that there's a third way. The administrator enters the route manually, called static routing. Could some nerdy guy type a route in? Absolutely. Is it legal to type a route in? Absolutely. Would that route be honored? Absolutely. There is such a thing as static routing. But most of the time, routers work 2 ways. When you turn the router on, it senses all the networks it's directly connected to. And after it's been on for a while, it talks to all the other routers and says, you tell me yours, I'll tell me mine, and it gets all the information. This is the one directly connected I sense to myself. This is the one that uses link state or distance vector, a routing protocol, and it tells me about it. Those are really the 2 ways it's done. Can you enter it statically? Yes, you can, but that's not very frequent and it's not done very much. All right? So I shouldn't have skipped that slide. Now I can move ahead. Okay. I'll do, yeah, now I don't know where I'm going now. Let's see, it's 3:58, 4 o'clock. Okay, the sexy hard part of the lecture is over. I probably have 10 or 15 minutes of what I call a little junk to put in, and we have to get to that, but we'll be done by 1:15 or so, okay? And I'm not doing this lecture ever again. Access control list, a set of rules what can go through, packet filtering. Now watch. If I want to filter packets, like you're a crook, I don't want to let you in. You know what I'm going to use? A firewall. A firewall says, you can come into my network, you can. You're always allowed in, you're never allowed in. You're a shifty character, you're a wonderful person. Anything from you, come on in. Anything from you, get lost, I don't like you. That's a firewall. That's a packet filter. But if I take a router and give a router an access control list, a router becomes a packet filter. So here's how it works. When your packet arrives on a router, the router has 2 mandates. First, it says, if I have a list, I've got to check. Are you on my list? Yes, I'll let you through, or no, I won't. If I have a list, I have to check first. Well, I don't want you to check a list. Can you just let me through? Yes, I can under one condition. If you remove my list completely, then I'll forward all your packets. So if I look and say, is there a list? And you say, no, there is no list. You know what I'm mandated to do? I must process your packet in. So an access control list is a set of rules configured on a router's interface for specifying which addresses can come in and which addresses can't. Big cuidado, it is an option. If I put a list on, you must obey the access control list. If I don't put a list on, you can ignore it because it's not there, and you must process all the packets in. Okay? It's called packet filtering if it blocks it, and it only blocks it if it's there. If it's not there, it can't block it. Can I block packets with a router? Yes, only if I have an access control list. Well, I'm going to skip this, but here it is. I can block it by source, destination, protocol, everything. And I can do that legally. Here's my quick to the point lecture. Most of the time, I block it by what? Source address. Why source address? If it came from you, I think you're a crook. I don't want you coming in. If it came through you, I think you're the greatest person in the world. I always want to let you through. I think you're a piece of garbage. I don't want to ever let you in. I think you're a wonderful person. I want to let you in all the time. How do I find out who you are? By your source address. Can I block it by destination address or protocol? I can, but most of the time, if it came from you, you're wonderful, come on in. If it came from you, you're horrible, I'm not letting you in. And not by you by name, but by you by IP address. Okay, this is my, I'd like to skip this, but I'm going to do it. For some reason, I don't like the book because they often mix metaphors, meaning we're covering one thing and now they want to talk about wireless access point. If I take a wireless access point and I crazy glue it to a switch in a router, that's known as a wireless router. So a wireless access point is just a thing that sends signals. If included in that device is a router and a switch, so a wireless router is really a wireless access point, a regular router, and a regular switch all crazy glued together and working together. That would be a wireless router. Right? That's all we got to know, right? Unfortunately not. Okay. And what we're going to talk about is the second line and the bottom line. What is the SSID? The SSID is really the name of the access point. So here's what happens. I'm sitting in a cafeteria. I say, hey, Bergen Network, can you help me out? You know what I'm going to get? A deafening silence. Oh, hey, I'm a student here. I want to do wireless. Can anybody help me? You're not going to hear anything. You want to know why? Because unless you call the access point by name, by SSID, it's not going to help you. So now your device says, hey, access point labeled Bergen 13, can you help me? Now the access point says, yes, I can. You say, wait a minute, I called you 5 minutes ago. You ignored me. Why? Because you didn't call me. You called, I want help from somebody, and I'm not somebody. As soon as you said, hey, Bergen 13, can you help me? Now I'm going to help you. So I have to know the name of the access point, the SSID, if I want to do it. Okay, I have to do that. How would I know that? Well, the bottom line, by default, access points are configured to transmit the SSID, so any device can see the network. So watch what happens. You're now sitting in the cafeteria. You turn on your device, you want to access Bergen wirelessly. What you don't hear, what's happening is that access point is saying, I'm Bergen 12, use me. I'm Bergen 12, can anybody help me? I'm Bergen 12, I'm Bergen 12. So now what you say, hey, Bergen 12, can you help me? And he says, yeah, how'd you know my name? Well, you've been shouting out your name for the last 20 minutes saying, I'm Bergen 12. Does anybody want to use me? I want to use you. You know what I mean? You have to call the access point by name, by SSID. The access point transmits the SSID, broadcasts it, so somebody then will be able to call it up. So how did I know to dial up Bergen 12? Because Bergen 12 was sitting there saying, I'm Bergen 12, does anybody need help? I'm Bergen 12, I'm lonely. I'm Bergen 12, use me. Okay, Bergen 12, I want to use you. How'd you know my name? Well, you've been shouting it out for the last 20 minutes. The SSID is an alphanumeric name and number that applies to the access point itself. Oh, big cuidado, only wireless. If you're on a connected fiber optic network or RJ45 network, there's no such thing as SSID. If you're doing it with radio waves wirelessly, you have an SSID. Only wireless. Okay, the lecture is actually going to end in a few minutes, but this is tricky stuff I'm going to get to in a minute. Why can't you say mushy stuff to your girlfriend on the CB radio? And the reason is anybody can listen in. You say, well, wait, I want privacy. Let's all go to channel 15, and I'm going to say sweet nothings to my girlfriend. I don't want anybody listening in. It's friggin' radio. Anybody can listen in who wants to. You can't stop them. You're sending a radio wave to somebody. Anybody who is in the last around you is going to hear it. There's no such thing as privacy on the CB radio. Well, now you have a different problem. I got my wireless device, and I'm talking to the access point up there. What am I doing? I'm sending digital, but it's all radio. This nerdy guy next to me who looks like a harmless dweeb is really a crook, and he's eavesdropping and capturing all my packets. So if I'm doing banking or something important, he can steal my password and everything. How can I get privacy on the CB radio, privacy on the wireless? And this word here, encryption. If you could talk to your girlfriend on CB radio in code or in gibberish, it had to be decrypted or decoded, then people couldn't listen into what you were saying. And if I'm sending data to that access point, people can capture my signal. I can't stop that. But if that data is all encrypted, they're going to open it up and see GBXQI. What the heck is this guy saying? What's GBXQI? It's a secret code I got. So I want to encrypt the wireless signal to make sure I get privacy. Here it is, everybody. WEP, WPA, and WPA2 are wireless encryption processes. And here's what you have to know. Pay close attention. WEP is the old one, the weak one. It encrypts. It's called wired equipment privacy. It was invented so many years ago, and within weeks of being invented, some nerdy guy hacked into it. It's useless. It can be hacked into directly, easily. So then they improved it with the other two. Here's the other one. WPA is the good one, the strong one. It takes a long time to encrypt. It takes a long time to decrypt. But the fact that it takes a long time to decrypt and encrypt means it's very complex and complicated. And that means that bad guys can't hack into it. That means it's very secure. So here it is. I'm going to have a little speech on this in a minute. If you do encryption, WEP is the old one, the weak one, the one that nobody uses because it's been hacked into. WPA2 is the good one, the strong one, the one that is used all the time because it's too difficult to hack into and it can't be hacked. Now, I'm going to make a little speech on this. That's all you have to know. If you take my security class or if you take a wireless class, or if you take, I think, a Cisco class, you would have to know exactly what was wrong with WEP and why it was hacked into. You would have to know the problems with WPA and what the coding was and why it was hacked into. And here's the big drum roll. You would have to know why WPA 2 is so strong and exactly what encryption and encoding mechanisms it uses that makes it strong. So you will have to know this stuff eventually. And that's bad. Well, it's bad and it's good because when you know it, it's going to take you several hours to figure it out, but then you'll understand why it's good or bad. Here you're just memorizing that WEP is the weak one and WPA2 is the strong one. You're taking my word for it. It's true, but you're taking my word for it. I don't believe you, Professor. Could you give me more details? Well, not now. I'm not going to know. But if you take the security class or the wireless class, you'll wish you hadn't asked because you'll get all the details and you'll have to know it for one of my tests. What are we encrypting? Only wireless stuff. We don't need to worry about this on a wire. This is radio waves. WEP is the old one, the weak one. WPA2 is the good one, strong. Now, the lecture's gonna end in a few more slides, but there's a couple of other things I want to do that's kind of sexy. I also want to do security. So security can be encryption, authentication, MAC filtering, and all of them. Encryption is the big one. I'm encrypting it so you can't eavesdrop. I'm encrypting it so if I'm sending my bank account password, you can't steal it and listen to it because it's in code and you can't read it. The guy I'm sending it to can read it, but because you can't crack WPA2, you can't read it. Okay? It says use the highest level you can, and that's WPA2. But the one I'm going to talk about because it would make a lot of sense is this guy, the MAC filter. So let's say I decide that I'm super stingy. I don't want to pay for any wireless. So I find one of my students who's a sucker. And I say, could you tell me where you live? Oh, I live on 294 Oak Street. Good, that's great. Have a nice evening tonight. So what I do is I drive to your house. I park outside your house and I tap into your Wi-Fi thing. You say, wait, I didn't invite you to do it. You can't come into my house. I don't have to come into your house. If I sit on the sidewalk outside, radio waves pass through buildings, pass through everything. So I could sit on your front lawn. I could even sit down the block from you, and I could probably access your wireless access point in your living room. Wait, I'm not inviting you in. Well, how are you going to stop the radio waves from coming in and out of the walls? Radio waves don't have anything. Now, if I try it from 10 blocks away, it's not going to work. But if I try it from your driveway or the sidewalk in front of your house, I might be able to do it. How could you prevent me from doing it? Well, one way you could do that is MAC filtering. So watch what happens. You all know what a MAC address is, and you all know what makes it unique. It's the burned in address. In other words, it comes with the device. So what you're going to do is you're going to have your wireless access point have a list of what they call legal MAC addresses. Who lives in your house? You live there. Grandma lives there. Uncle Herman and Aunt Gertrude live there. And they all have little devices. So you put in grandma's MAC address. You put in, it's similar sort of, I think. I heard what you said. You put in a legal MAC address. So if grandma, Aunt Gertrude, or Uncle Harry all try to log in, they can. Now, I come to your front lawn and I try to log in. Well, my MAC address is 2B8C74. The MAC filter goes down the list and says, I don't see that in my thing. So get lost. Now, wait a minute, let me in. No, there's 5 legal MAC addresses. Your MAC address doesn't match what I think is legal. I never heard of you. So even though you may have a signal, and even though you may be able to connect to my wireless device, I'm not going to let you in. Why? Your MAC address doesn't match my list of authorized MAC addresses. When Aunt Gertrude or Uncle Herman tries to log in, oh, I see your MAC address on my list. Come on in. Okay, I see yours. Come on in. When mine tries to get in, you say, I don't see it. They're not going to let you in. Now, let me stop. That's simply a way to do it. It's an option. Do all wireless devices do this? Of course not. Why? Because someone didn't configure it. But if you wanted to take your wireless access point, and if you wanted to apply MAC filter, and you wanted to use software to give it the names of the MAC addresses that are legal, and then you wanted to tell it, don't allow any other ones in, then it would do that. You would have to tell it to do it. You have to give it the list of MAC addresses you wanted to, and it's one way or a way to do that. Add the MAC addresses of the wireless devices allowed to access to the list. If anybody else tries to get in, they can't. I only explain that because I think it makes a lot of sense. And it's another use of a MAC address, which is the same MAC address we've been using all along. Okay. Again, I'm not happy that they're doing wireless at the same time. They just finished doing routers and switches, but I mean, this is what they want to do, so I'm following. you might want to know on the test which of these is secure and which of these is not. All right, I know we're getting 411. I'm getting tired. I want to see where we're going on this. If there's anything else I want to cover. Actually, I can do this one. I don't know if I want to, but I can do it. And I'm going to, even though, and then we'll stop. Network interface card, top dot. You never replace your NIC card. It's built in, you just use it. Why would you want to replace it? The top dot. I got a slow NIC card. Well, I can't take my NIC card and make it faster. I'm stuck. So what I might want to do is put another NIC card in that's faster. I'm leaving mine where it is. It's slow. I'm going to put another one in that's faster, and I'm going to use the other one instead of mine. By the way, every time I put in a NIC card, what do I get? I get a new MAC address because the MAC address comes with the NIC card. Right? What makes a NIC card faster? This stuff, which I'm not going to talk about, and this, which I am. Let me just talk about these, and then we'll stop, I think, after that. I want a better NIC card. I want it to go faster. How can I do it? Let's start with bus mastering, and we'll try the RAM buffering. Normally, when data comes in, it comes into my input-output port, and I'm putting the data in my memory. So I'm loading a term paper from my input-output port into your memory, so it just goes directly in, right? Well, sort of. Think this. Here's the first byte of data. I'm the CPU. I put it in this part of RAM. Here's the next byte of data. I'm the CPU. I put it in this part of RAM. Here's the next byte of data. I'm the CPU. I put it in that kind of RAM. So I'm taking each byte, looking at it, putting it in RAM. Could you speed that up? No, I can't. I got to look at it. So what's bus mastering? Instead of the CPU, microprocessor, putting every bit of memory into the, every bit of data into the memory, it's automatically done. In other words, you tell the CPU, take a break. The NIC card will simply filter all this data straight in. Instead of the CPU taking byte 1 and putting it in, the CPU taking byte 2, putting it in, the NIC card says, okay, people, just come right into memory and bypass the CPU. What does that do? Faster. Permits a network adapter to take control of the computer's bus to initiate and manage data transfers to and from the computer's memory. Now, what is our purpose? I want to go faster. What does bypassing the CPU do? It makes the data come in and out faster. We're done, right? One more. What is RAM buffering? This one you'll see right away. The data is coming so fast, I can't control it. Amazon delivering packages to your door so fast that the package is spilling off your porch onto the ground. There's packages in the rose bed because you can't get them in fast enough. So what I'm going to do with RAM buffering is the following. The data is coming in so fast that I can't get it into memory. I'm going to have extra RAM on the NIC card that's going to store the data in transit. So instead of the packages on your front porch going to your rose bed or your frog pond or something, they'll all be stored in a certain area where you can then process them into your house. RAM buffering. The network interface card includes additional memory to provide temporary storage for incoming and outgoing network. That's coming fast and then can be sent out as fast as it's coming in. One more time. The data is coming in so fast, I can't process it. With that extra RAM in the network interface card, I can temporarily store it there. And as soon as I got the other stuff processed in, then I can put that in on the way in and I don't lose any of it. Now, what would happen if that extra data is not there? I got to say, don't send me anything more. I can't take it. I just get rid of this stuff. Don't send it till later because I can't process it. With the RAM buffering, I can send as fast as you want. I'll just store it here until I do it over there. There's 5 more. I'm not going to do them all. What do all these things add up to? A network interface card that's faster. What does that mean? Data comes into my computer a lot faster, and data goes out of my computer a lot faster. Okay? All right. I don't even know what time it is, but. Okay, let me just see if there's anybody I missed. So here we are. Next week, we'll Latif and Lewis. I didn't get you. I make sure you're there. Latif and Lewis. Good. Next week, we're going to be doing chapter 9. And then the week after next is a review for a test the week after that. So just before Thanksgiving, there will be a test on 7, 8, 9. We just finished 8. And I warned you what was on some of these tests that might be on chapter 8. Okay, I'm done. I'm taking attendance. You can all go home. And Latif and Lewis, I'll get you both in. And if anybody wants to stay and ask me a question, they can. I'll see you next week. Okay?
Have a good afternoon, Professor.
Oh, Grandma, good to see you. Yes, glad you can make it.